Welcome to this video. Today we will be discussing three problems from complex numbers, and these problems will be based on high school level and up to the undergraduate first year level, and we will be discussing problems based on Euler's theorem, de Moivre's theorem, and also the basic properties of modulus and different properties that complex numbers prescribe. Okay, so the first problem here is this. We are given that z1 and z2 have each modulus equal to 1. So basically mod of z1 and mod of z2 is 1, and z1 z2 is not equals to minus 1, which is obvious because otherwise this expression would not make sense. We have to see and prove if z1 plus z2 divided by 1 plus z1 z2 is a real number or not. So it's kind of a prove disprove problem, but I have actually modified a bit so that we have to directly prove it is a real number because it indeed is. Now, in the solution, we are given mod of z1 equals to mod of z2 equals to 1. Note that whenever you have mod z equals to 1, this means that z lies on the unit circle. So remember this fact that if you have a circle like this, which has the center at the origin, and if you have the radius of the circle as 1 unit, whatever measurements you are taking in, either centimeters, meters or feet, so this is called the unit circle, and this is in the Argand plane. This is called the real axis, and this is called the imaginary axis. And this complex number resides on the circumference, somewhere on the circumference of this circle, which is what we mean by the statement lies on the unit circle. And if you rather were to write mod z equals to a, this would mean it's a circle centered at origin with radius a. So complex geometry is not something very hard, but it basically translates Cartesian equations to complex numbers. Now, in order to approach this problem, we will let t equals to z1 plus z2 whole divided by 1 plus z1 z2. And we want to first find out what is the imaginary part of t. Why are we taking this approach? Because we know that we have to prove that this expression right here is a real number. And if it is a real number, then obviously its imaginary part should be 0. Something to remember is z into z bar is always equals to mod z whole squares for all complex numbers z. So this is a very important equation and we need to remember this. So let's begin. We were given the modulus of z1 and z2 equal to 1. So of course their squares would also be equal to 1. So this equation must make sense. And since we know this property, z into z bar is mod z square, we employ this into this equation to get the following: z1 into z bar is equals to z2 into z bar is equals to 1. Now start with t, z1 plus z2 whole divided by 1 plus z1 z2, right? From this two equations and equating them to 1, we can get that z1 is basically 1 by z1 bar, and similarly z2 would be 1 by z2 bar. Using this, we can get 1 by z1 bar plus 1 by z2 bar whole divided by 1 plus 1 by z1 into z2 whole bar or z1 bar into z2 bar. Remember, conjugate can be extended individually or be grouped whenever multiplication has happened or division has happened in case the denominator is non-zero. So we simply apply the fact that z1 is 1 by z1 bar and z2 is 1 by z2 bar and write it like this. In the next step, we multiply z1 bar and z2 bar both in the numerator and to the denominator. So when we do the multiplication, we are simply left with this expression. As you can do the multiplication yourself, it's very pretty common and basic. Now z1 bar plus z2 bar can simply be written as z1 plus z2 whole bar, because you are simply taking the conjugate, and again conjugate is distributed among the plus and minus. And similarly 1 plus z1 z2 whole bar is simply 1 plus z1 z2 whole bar, because you can simply again take the conjugate, and conjugate of 1 is 1 itself because 1 is a real number. Now again, as I told you, conjugates can be distributed over division, which means that z1 by z2 whole bar is nothing but z1 bar by z2 bar for any complex numbers z1 and z2 where z2 is not equals to 0. Something to remember. And this means that we basically have arrived at the definition of t itself, except now it is the conjugate of t. So basically we get t equals to t bar. This is a very important equation for us, and we will name it equation 1. And from this equation 1 we can get our answer. Recall that imaginary part of any complex number is simply z minus z bar whole divided by 2i. This means that imaginary part of t must be t minus t bar whole divided by 2i, which is 0 by 2i, and we get this from the equation 1. Therefore, the imaginary part of t is 0. Do not be confused using the modulus sign and the modulus value of a complex number and the complex number itself. Remember that they are connected using this relation, and it is nothing else. Mod z whole square is simply a real number. It is not a complex number. It's not an imaginary number. And whereas z could be a real number, could be an imaginary number, could be a complex number, right? Okay, let's get to the next example. Okay, this is another pretty simple type of equation, but it requires some effort to solve it. Find all complex numbers z such that z cube is equals to z bar. So the statement is pretty clear, and we would proceed from our knowledge that z into z bar is equals to mod z whole square, from which we can say that z bar is equals to mod z whole square upon z. This is important, and this can be done only when z not equals to 0. We realize that z equals to 0 is a very trivial solution of this equation, so of course we will mention it at the very end, that yes, of course z equals to 0 is a solution, but right now we do not need to employ that solution inside this problem, and we would rather assume that z is not equals to 0 and proceed with that. Now then, z cube, from the equation that we were given here, z cube equals to z bar, we can simply put z bar as mod z square by z and then multiply z on both sides to get z to the power 4 equals to mod z whole square, which is a real number. Let's call it a, and where of course a is greater than 0, since mod z whole square is greater than 0. See how I am exploiting the fact that mod z whole square is nothing but a real number. Now let us assume a new complex number q, which is defined as z, which is a complex number, multiplied by a to the power minus 1 by 4, where a is the real number that we just defined. Since a is positive, that is why the fourth root of a should also exist, because it's a positive real number, right? So this allows us to conclude that, let's call it equation 1 actually, q to the power 4 is nothing but, put in the value, z into a to the power minus a by 4 whole to the power 4. Now you use the distributive law for exponents, z to the power 4 into a to the power minus 1 by 4 whole to the power 4. Now z to the power 4 is nothing but a, as we had defined earlier, you can see here, equals to a, and then a to the power minus 1 by 4 whole to the power 4 will equal to a inverse. Since a is a real number and a greater than 0, a inverse exists, and a into a inverse, which is 1 by a, essentially in this case of real numbers, is basically 1. So therefore q to the power 4 equals to 1 is the equation. This reminds you of the roots of unity. So solutions to this equation 1 are basically the fourth roots of unity. Now the fourth roots of unity are very basic and common. You should know it by heart if you do not know yet. Those are 1 minus 1 plus I minus I. These are also called units in some algebraic fields, since you understand that these numbers are what makes up the entire complex and real numbers, right? So I and minus I are enough to make them, and 1 and minus 1 are also enough to make them. So that is a discussion for a completely entire topic, which is called algebraic number theory, and we will not talk about it. But yeah, notice that they are called units there. Anyway, so these are the values of q, right? Now we can put the value of q, which we had assumed earlier, which is z into a to the power minus 1 by 4, which is equal to these four values. Then you can multiply a to the power 1 by 4 on both sides simply to get the value of z, like this. Now we do not want the answer in terms of a, right? So notice in the first equation you can always take modulus on both sides, and this is again true for any complex number. You can always take modulus on both sides. So once you take mod of z cube equals to mod of z bar, remember that modulus of a conjugate is same as the modulus of the complex number itself. So first of all, mod of z cube is nothing but mod z whole cube equals to mod of z, because mod of z bar is nothing but mod of z itself. Take everything to the left hand side, take mod z common, and you get this. Since z is not 0 as we have assumed, we must have this quantity as 0, which means mod z square is 1, and now we also know that mod z square was a, so a is basically 1. So the values of z which satisfy all these equations, this equation z cube equals to z bar, are 1, minus 1, plus I, minus I, and 0. These are all the solutions possible. Now let's go to another problem. Find all positive integers n such that this equation is satisfied. 1 plus I root 3 by 2 whole to the power n plus minus 1 minus I root 3 by 2 whole to the power n equals to 2. Now, you must notice, if you know the cube roots of unity, that this is called omega and this is called omega square. You can try and proceed from there, but what I would suggest is to do it this way first to get a clear understanding of how polar form of complex numbers and how Euler theorem works. So first of all, write minus 1 plus I root 3 by 2 like this, and use the fact that minus half is cos of 120 degree, which is cos of 2 pi by 3, and root 3 by 2 is sine of 120 degree or sine of 2 pi by 3. And then use the Euler's theorem or Euler's formula, right, which is nothing but e to the power I theta is equals to cos theta plus I sin theta. So basically, if you have cos theta plus I sin theta, you can write it as e to the power I theta. Here theta was 2 pi by 3, so we just simply wrote it as e to the power 2 pi I by 3. Similarly, minus 1 minus I root 3 by 2 is equal to e to the power minus 2 pi I by 3. Then, using this 2, we can write e to the power 2 pi I by 3 whole to the power n plus e to the power minus 2 pi I by 3 whole to the power n is equal to 2. And again, simply you can just take the exponent and absorb it inside by multiplying it. It simply gives you e to the power 2 pi n by 3 plus e to the power minus 2 pi I n by 3 whole divided by 2 equals to 1. Notice the formula that cos theta is equals to e to the power I theta plus e to the power minus I theta by 2, something which you should, I think, memorize again. This is something that you are going to use a lot of times while doing complex number problems, and this also can be derived directly from this Euler's formula. Just try putting theta as minus theta and then add the two equations. Now, from this we can conclude that this equation is nothing but cos of 2 pi n by 3, because we just use the formula here, right? Now, when is cos 1? Cos is always 1 at integral multiples of 2 pi. So basically cos 2 pi is 1, cos 4 pi is 1 and stuff like that, and then cos 0 is 1, right? So cos 2 pi m is always 1 for all m belonging to integers, whether it is positive or negative, it does not matter. So this means that n here, we already have the 2 pi, but there is an n by 3 here, so n must be a multiple of 3 for this equation to be true. So n should be 3k. So all integers which are multiples of 3 are answer to this equation, and thus we have completed this problem as well. So this problem was very nice, and it was based on Euler's theorem. And the second problem, we learnt about roots of unity and also the modulus applications of modulus formulas. And in the first one, we learnt about real part and imaginary part and how to manipulate between them using properties of conjugate and modulus. So I hope you like this video. Let me know in the comment section if there is any doubt you have. We'll see you in another video.